Are we alone in the universe? You know, for the longest time, when we've thought about finding life out there, we've pictured alien signals or maybe tiny fossils. But what if the biggest clue, the most profound clue, isn't any of that? What if it's just a rock? A simple, dark, magnetic rock?
I mean, think about it. For years, we've been searching Mars for signs of things that were alive. But what if we've been asking the wrong question? What if the real secret isn't in what lived, but in the chemical engine that could have started life in the first place, an engine powered by a very common mineral?
So yeah, forget the fossil hunt for a minute. We're going on a chemical investigation. We're going to follow the breadcrumbs locked inside the geology of Mars itself to see if the planet ever really had the right stuff, the right conditions, to spark life from scratch.
So where do we even start? Well, our first clue actually comes from way up high, from satellites that have been mapping Mars for decades. They found these weird, powerful magnetic signals coming from the really ancient Southern Highlands. Now, this is strange because Mars's global magnetic field died billions of years ago. So what magnetized these rocks?
Well, the best hypotheses we've got points to a fascinating process called serpentinization. It's basically a chemical reaction between water and certain kinds of rocks. And here's the kicker. As a byproduct, it creates one of the most magnetic minerals in nature, magnetite.
So, what exactly is this life-making rock engine? I mean, it sounds pretty epic, right? Well, it is. Serpentinization isn't just some geological quirk. It's a fundamental process that can completely change a planet's environment, unleashing the very energy and ingredients that life needs to get going. To put it simply, serpentinization is what happens when water soaks into rocks that are rich in a mineral called olivine, which is super common, by the way. This kicks off a chemical reaction that totally transforms the rock. And more importantly, it transforms the environment around it in some really profound way. Okay, let's break it down. It's a three-step dance. Step 1, water gets into that olivine rock. Step 2, a powerful chemical reaction starts, totally changing the rock's internal structure. And step 3, you get three amazing things out of it. The rock turns into a new mineral called serpentine, you get our magnetic clue, magnetite, and critically, you get a huge release of pure hydrogen gas. And this, right here, is the core of it all. You start with two of the most basic things in the cosmos, rock and water. And through this process, you create not only altered rock and a magnetic signature, but also a potent source of chemical fuel in the form of hydrogen. This isn't just about making rocks, it's about making the fuel for biology.
Now, you might be thinking that magnetite is just a passive byproduct, right? Just the magnetic clue we were looking for. But it turns out, in this story, magnetite might just be the star of the show. Think of it less as a clue and more as a microscopic chemical factory.
The surface of a magnetite crystal is just incredible. Its structure makes it a fantastic catalyst. You could call it a molecular matchmaker. It literally grabs simple, boring molecules from the environment, holds them in just the right way, and forces them to react and build new, much more complex molecules, the very building blocks of life.
And here's the playbook for how that factory works. At the very top, you see serpentinization, creating the magnetite. But then, that magnetite becomes the factory floor for all these other critical reactions. It's driving multiple chemical assembly lines all at once, turning simple gases into the complex stuff of biology.
And out of all those assembly lines, two are just absolutely crucial for life as we know it. One process uses all that hydrogen to build hydrocarbons. Those are the backbone chains of all organic molecules. And another process creates ammonia, which is a non-negotiable ingredient for building amino acids, the little links that make up proteins.
Okay, this all sounds like a fantastic theory for Mars, but how do we know any of this actually works? Well, we find the crime scenes right here on Earth, places where this chemistry is happening right now, or where it happened a long time ago. We call them terrestrial analogs.
And scientists go to all these incredible places. In the Duluth complex in the US, they're learning how iron-rich rocks can churn out tons of magnetite. Over in Oman, they can see how the specific chemistry of the water creates these little localized hotspots for reactions. And in places like Sri Lanka, they're studying different kinds of rock to see how the starting ingredients completely change the final product. And look, this isn't just some abstract idea on a chart. These are the rocks themselves. What you're seeing here are samples of the greenish serpentinite rock and the dark, rich veins of magnetite that were collected from that site in Sri Lanka. This is our ground truth for what could have happened on Mars.
All right, but now we get to the big challenge, the potential elephant in the room.
This all sounds amazing, but the key ingredient is liquid water. And Mars today, as we all know, is a frozen, bone-dry planet. So how could this life-making engine have ever gotten started?
So, yeah, if all the water on Mars is locked away as solid ice, how could these essential rock-water reactions possibly take place? Well, the answer might lie in a kind of water that isn't really liquid in the way we normally think about it. See, the solution probably isn't a vast ancient ocean. It's something much, much smaller. You have bulk water, like a lake, which has to be above freezing. But then there's this other amazing thing called interfacial water. These are just microscopic thin films of water that can stay liquid between mineral grains and ice, even at temperatures way below zero. And believe it or not, these tiny, super cold films of water are all you need. They become these little reaction chambers. Inside these films, chemicals can still move around and react with the surface of the olivine, driving the whole serpentinization process and creating that crucial magnetite, even on a planet that seems completely frozen.
So let's step back. What does all this mean for the big picture, for our hunt for life out there? Well, it fundamentally changes what we should be looking for and where we should look.
Okay, let's connect all the dots one more time. We have a natural geological engine called serpentinization that creates magnetite. That magnetite then becomes a prebiotic factory, building complex molecules from simple ones. We've seen this exact process happen all over Earth, and now we have a plausible way for it to work even on a cold Mars, thanks to those thin films of water. And this idea completely changes the game for huge missions like the Mars Sample Return. The ultimate goal isn't just to find one tiny microscopic fossil anymore. It's to find the factories themselves. Finding a big concentration of magnetite in just the right kind of ancient rock on Mars, that would be like finding the workshop where the building blocks of life were being mass-produced.
When you really think about it, this suggests that the potential for life might just be baked into the fabric of rocky, wet planets all across the universe. The ingredients, water and olivine, are everywhere. The factories, magnetite, can build themselves. So the real question isn't whether a planet like Mars could have had life, it's whether that incredible planetary engine was ever switched on.